Video would be learning a different form of conversion from one base to the other bases. Now, to do that, we need to understand the conversion table. Here we have a conversion table of all the four bases, that is the binary, hexa, octal, and decimal. Now, how this table is constructed? This table is constructed in the form of 2 to the power n, where n is having the value 4. Why? Because we have the highest base value, that is of hexa, which comprises of 16 values. So 2 to the power n, if n becomes 4, then we have 16 values. So that is how the binary construction of base values are done. So now we have decimal values starting from 0 to 15, comprises of 16 values. We have octal from 0 to 7, as we only have 8 values for octal, that is from 0 to 7. And then we have 10 to 17, as we don't have 8 and 9 for octal values. And for hexa, we have 0 to 9 and then capital A to capital F. Now let's see the comparison of these values and the conversions of this value, or the equivalent of these hexa values or the decimal values or octal values with respect to binary values. Now this is the most important part of this table. Why? Because this is a group of 4 bits of values that we are constructing, as because the power of n, as I said, is 4. 4 comprises the bit of the particular binary system, as binary values only comprises of 0 and 1, hence they are called as the bit values. Now, to construct this table of binary values, as you know, we have to have 16 values. So the first bit comprises of the first 8 zeros and the next 8 ones. The next bit compares of first 4 0 and the next 4 1, next 4 0 and the next 4 1. This is how the pattern follows. The next bit has got 2 0, 2 1, 2 0, 2 1, and that's how it follows. And the last bit is having 0 1 0 1 0 1. Okay, so this table is used to basically convert binary to octal and hexa to binary, as because for conversion of decimal to binary we have learned the LCM process. Okay, for 0 to 15 you can use this table, but above 15 you then need to use the LCM table. Okay, now for example, the hexa equivalent of A, capital A, is 1010 of binary. The hexa equivalent of capital B is 1011 of binary. Similarly, the octal values, the binary equivalent of octal 7 is 0111. So that is how the conversion table is used to convert hexa to binary, octal to binary, or binary to hexa and binary to octal. So in this part, we'll be learning about how to convert an octal number to a binary number and a binary number to octal number. Now, in the previous table, we have learned the conversion of a 4-bit binary value to a hexadecimal value, a octal value, and a decimal value. Now, here we'll be using a 3-bit binary value corresponding to the octal value. Why? Because octal is having numbers starting from 0 to 7, that is 8 values. So 2 to the power n, if we put the value of n as 3, so we get a 3-bit binary order. Okay, so now we'll look into how we can convert octal to binary and binary to octal. So these are 2 examples being given. So let us look into the first example, that is conversion of octal to binary. Now we have got a octal value, that is 3674, which will be converting to binary value. Now this is a very simple conversion, unlike the other conversions that we have done where we have got a bit of mathematics to deal with. Here we only look into the table and do the conversion. Now, to convert 3674 base 8 to base 2, let us first arrange 3674 as we have arranged here, and then with the table, with the help of the table, we'll collect the value of each octal to its corresponding binary. For example, the octal value 4 has a corresponding binary value as 100. So we'll always do the arrangement from right to left. So here 4 is 100. As you can see, the octal value 4 is having the binary value 100. 7, we are having the binary value 111. 6, we are having the binary value 110. 3, we are having the binary corresponding value as 011. And then we arrange it. So therefore 3674 base 8 is equivalent to 011, 110, 111, 100 base 2. So this is how we convert octal to binary. Now let's move to the next one, which is the binary to octal conversion. So when we have a binary to octal conversion, for example, we have a value 111010 base 2 to base 8. Now we have to arrange it in the form of 3-bit values starting from right to left. So here you look, I have arranged it in the form of 3-bit values starting from right to left. So we have taken 010, 1 3-bit, we have taken 111, the other 3-bit. Okay. Now the corresponding value of 010 binary to octal. So 010 binary to octal is 2. We have mentioned it. And 111 binary to octal is 7. So therefore 111010 base 2 is equivalent to 72 base 8. So these are the conversions of octal to binary and binary to octal. Now let us look into the binary to hexadecimal conversion and hexadecimal to binary conversion. Now if you look into the first table that we have used a 4-bit binary conversion. We have used a 4-bit binary table rather, where we see the corresponding values of hexadecimal. Now again, to convert binary to hexa and hexa to binary, we will be using that table. Here we have a value which is this length. Okay. Now we'll arrange the value in 4-bit starting from right to left. Now look, that is how we have arranged. We have got first 4-bit as 1110, second as 1010, third as 0111, and the fourth one as 11. Okay, so that means we have to fill more 2 values to form it a 1 4-bit value. Now when we have this kind of a scenario, we will always fill the values with zeros, okay, not 1. So that is why we have filled this 1 4-bit with 2 zeros. Now the corresponding value of this binary with respect to the table that I have shown previously would be 1110 is having the E as a corresponding hexa value, 1010 is having A, 0111 is having 7, and as because we have put 2 more 0, because we are left with 2 more to form 1 more 4-bit, and it is 3. So that is, we have 37AE base 16 as the value corresponding to binary to 16 in this conversion. Okay, now let's look into the second one, that is hexadecimal to binary. The same thing. We have a hexadecimal value as 4A8C base 16. Now we'll again arrange it C4A8C. Now we'll find the corresponding value of C from that table as binary. So we have 1100, for 8 we have 1000, for A we have 1010, for 4 we have 0100. So this is the corresponding binary value we have with respect to the hexadecimal value 4A8C. So this is very simple. Okay. Now we have one more conversion which is again very simple. That is to convert a hexadecimal value to octal and vice versa. Now we do not have a direct method of conversion hexadecimal to octal and vice versa. To do that, what we do is that we either convert hexadecimal to binary and then convert binary to octal. That means we convert hexa to binary and then we convert the binary to octal for hexa to octal conversion and vice versa. Similarly, for octal to hexa conversion, we have octal value, we convert it to binary and then we convert it to hexa. So that is how we do that conversion. Thank you for watching the video.